All right, so what we're going to look at today are two kind of specific problems. So like there's a problem where you're trying to find a point that is the closest distance to a function, and then there's going to be a separate problem where we have to use the Pythagorean theorem. Hopefully that one goes well. I probably should have done that one this morning instead of messing around with that computer over there. But we'll do it as we go along, and it will be good. This one I know is good on it, and we actually have a little bit of a shortcut we can take on this. So basically, any formula, any equation that you learn in math, or a lot of times even science, you can apply the stuff from calculus to, and that's kind of what this section is about. So example 6 is going to use the distance formula. We want to know what point on the graph of y equals the square root of x is closest to the point 5, 0. Okay, so we would measure the straight line distance from that point on the x-axis up into this line. So to give you an idea of what we may be talking about, maybe the answer is just go straight up to the curve. I did say line. Maybe the answer is to go, over here to the curve. But then again, based on how far I just drew that line, I don't think that's the answer, right? So it's definitely not going to be there. I'm pretty sure, we'll figure it out when we do it, I'm pretty sure it's not the straight line. I think you can get a little bit of a shorter distance by going up diagonally like this. And that's our goal. We just basically need to figure out where to go on the line to get the shortest possible distance. Okay. So we are going to use the distance formula from geometry. Does anybody remember the distance formula?
Square root of x squared minus x1 squared plus the
close
squared plus y squared.
Y2 is what you want to say.
Minus y1
yeah. So the distance formula is the Pythagorean theorem. So underneath the hood, it's the Pythagorean theorem. It's not c squared equals, but it's c equals. So that's why we're starting out with the square root. So instead of c squared, I'm going to use d for distance. But we're taking the square root of that. And it's just two things squared and added. But to get those two things, we have to actually subtract two coordinates. So it's x2 minus x1, but squared, plus y2 minus y1, but squared. So that x2 minus x1 is the length of a line. So it's the length of a side of a triangle. The y2 minus y1 is the length of a line. So it's the other leg, you can say this, it's the other leg of a right triangle. And that's, and then we took the square root of it. Yep. Oddly enough, we are going to go back to the other form of where we actually will square both sides and make life a little bit easier in the middle. So let's get this thing filled in. Let's get the function we actually have to minimize. We have 2 points. Our first point is going to be the point 5, 0. Correct. And our other point is some generic point on the curve. We did this in some, I'm trying to remember which problem we did this in. Did we do this in, yeah, we did this with related rates too. So since we have a y equals equation, we're going to write that second point as x, y, but we want it in terms of one variable. And since y equals the square root of x, if you're on that curve, we're going to write it as x, square root of x. Make sense? Y equals square root of x means you can literally use square root of x where you would normally put y. And that generic point is x, y. Okay, so we will fill these into our formulas. It makes the most sense to keep the numbers as our x1 and y1 because we're going to have -5 and -0. It'd be better to have minus a number than minus a function. And the distance from, and here's what we're finding here. In this, we are writing an equation that finds the distance from the point 5, 0 to any point on the line. So it's a specific formula for our case, and that's basically just going to be the square root of x minus 5, but squared, and then plus square root of x minus 0 squared. So the fact that our point is on the x-axis actually is going to make this a lot simpler because square root of x minus 0 is just square root of x, and then we get to square it. So otherwise, we'd have to do some kind of foiling, which would have left us with some other stuff. So this problem is slightly easier because that y coordinate is 0. All right, so let's simplify that. We do have to FOIL the x minus 5 squared, so that's going to be x squared minus 10x plus 25. And then we have the square root of x squared, so that's just going to be a plus x. Yes. So we end up with our distance formula being this, the square root of x squared minus 9x plus 25. Okay. We need to minimize that, right? We want the smallest possible line. We should end up in a situation where the distance is decreasing and then it starts increasing again, right? This is going to be an endpoint, which would be larger than the actual distance when I get to my point. And when I do hit the minimum, now that distance is going to get bigger and bigger and bigger. So we are going to be in that situation where we just have one critical value and the signs do the thing we need to it. Here's the other thing. This function, if you think about it, what's kind of going on here is we have our x coordinate, we plug it in and we get a number, and then we take its square root. We want this thing to be as small as possible. We can get away with just figuring out when the polynomial is as small as possible because the square root of that number will be smaller than any of the other numbers. So as long as the polynomial reaches a minimum, then the square root of that polynomial will be at a minimum. So yeah. Yep. That is a D. Those are all Ds. So yeah, that one looks like a D. Yeah, D for distance. Okay. So with these distance problems, once you get that distance formula, you can minimize just the polynomial. And we'll call that D squared. So in a way, we are kind of writing the Pythagorean theorem. So D squared is what we want to minimize here. And I'll give you a short backstory too, calculus-wise, why it kind of does the same thing as well. And that's actually not too difficult because all we have to do is find D squared prime and find its critical values. And looking at that guy, they're going to be really nice. So we'll call it D squared prime. Hey, it's an easy one for once. Derivative of x squared is 2x. Derivative of minus 9x is negative 9. Derivative of 25 is right. So we want this thing to equal 0, and that happens when x equals 4 before and a half, 9 halves, both correct answers. Now, let's say this was 2 years ago and I was teaching this for the first time and I didn't realize that shortcut was there. Minimizing D squared instead of minimizing D. I may have told my students that we needed to find D prime. Don't write this down. Don't write this down. Okay. So we're minimizing D prime. I called it of x, but we're not writing it down, so I used an extra piece of notation there. That would be a chain rule problem, right? So the first thing we'd have to do would be to find the derivative of the argument, which is the polynomial. Agreed? And that would still be 2x minus 9. That would be multiplied out front, but we're going to end up with a fraction here so we can bring it up to the numerator. We've seen that in a few different cases. And then the derivative of the square root is just 1 over 2 square root of x squared minus 9x plus 25. Don't those two things have the same zeros? The only way a fraction is 0 is if the numerator is 0, right? So we'd be in the same spot where we'd be saying, well, we need to figure out when 2x minus 9 is 0. We'd have the additional thing where we'd have to look at this polynomial, which doesn't factor well. I don't know whether it's, it would definitely add some complications to it, but we don't need to do that because we just need to know when D prime is 0. I feel like either this ends up being outside of the domain or something ends up being a max somewhere out here. I don't remember off the top of my head. But the key is, either way, we had to find out when 2x minus 9 equals 0. So we're going to take the shortcut on our distance problems and minimize d squared instead of minimizing d. All right, we erase that. Last thing we have to do is make sure we've answered the question. We definitely found the x value. We should draw the sign chart. That should be super easy, easier than finding an eraser, apparently. That was what I was struggling with there. Excuse me. But we are doing a sign chart for 2x minus 9. So that's the most straightforward sign chart you can think of. 9 halves, negative before, positive after, which is exactly what we want to have happen if we're looking for an absolute minimum, right? One sign change, and that sign change goes from negative to positive. So we do have a absolute minimum when x is 9 halves. The question says what point on the graph. So our point is 9 halves, comma, root 9 halves. Yep. Which is a great, great final answer. If it were multiple choice, it might be written like this. Because you can, as long as it's just a number over a number, you can root the numerator, root the denominator, and 9's a perfect square. That's also a possibility too, but we don't rationalize as much in calculus. So, but yeah, that is a third correct answer. But none of it is, so that takes us back to rationalizing, because we don't, in pre-calc, we don't like the root under the denominator. So we multiply top and bottom by root 2 over root 2, which gives us a regular 2 in the denominator and a new root 2 in the numerator. All of those are correct answers. They all represent the same number. So, questions on that? That one's not too bad. It could be worse, but not too much. Depends on the function. You know, the function wasn't super complex. Cool. Alrighty. Example 7. Fingers crossed on this one. I remember trying to do this one last week and giving myself a little grief on it. Let's see how it goes. This one we're going to use the Pythagorean theorem on, which I guess that's what we did. The distance formula is the Pythagorean theorem. We got a picture to go along with this one to really point it out. A small island is 3 kilometers from the nearest point P on the straight shoreline of a large lake. So that P is on the shoreline. If you measure straight across, you get to the island. We do have a right angle here. A town is 12 kilometers down the shore from P. If a person on the island can row a boat at 2.5 kilometers an hour and can walk at 4 kilometers an hour, where should the boat be landed so that a person arrives in town at the shortest time? There's a couple variants of this problem. I think this is the harder one, so you guys have the little bit of an easier one to do in the work, but it is different. Think about what's going on here. If I decide to just row straight across, and am I walking or running, and then walk, that's going to take an amount of time. If I row diagonally, I have less walking to do. But I walk faster, right? So there is kind of like some sort of happy medium in the middle here where I row a little bit longer than I would have to just go straight to point P and then walk the rest of the way. That's kind of what's going on in this problem. Obviously, a full row is going to be the most amount of time because of how slow you row. And then doing the largest possible distance is also going to take too much time. So there is somewhere in the middle. Okay. So we need to do some labeling here. That 12 is the full distance from the town to point P. So basically, what we need to do is we need to label, we kind of need to break it apart. And I think the best way to do that is to label this part of it X. And then what would the red line be? Too hard. No, how about there's 2 red lines. Let's start with the easy one. What's that red line? 12 minus X, yes. Yes. I was about to tell you no, but then I realized I said red line and there were 2 of them. Yes. Cool. Okay. So yeah, so we have that broken down into x and 12 minus x. That could have gone the other way. I could have labeled the first part 12 minus x and the second part x, but I'm going to use the Pythagorean theorem inside of that smaller triangle on the left. So it's better to have the x here because I'm going to have to square it, and I'd rather square x than 12 minus x. Make sense? Yeah. So Jack, now you are definitely getting the right answer. Using the Pythagorean theorem, you were jumping. I love the fact that you can jump there. The Pythagorean theorem tells us that this red line here, which I am going to recolor as blue. Yeah. Yep. It is the square root of x squared plus 9. That comes from, let's call this c. This comes from c squared equals 3 squared plus x squared, which is 9 plus x squared. So that c is the square root of 9 plus x squared. No, I didn't. I gotta remember to take attendance when I'm done with the notes. Morning. So I'm going to unmark that as c and mark that as 9 plus x squared. Not 9 plus x squared, but the square root of 9 plus x squared. Sure. Cool. All righty. Okay, so we know the lengths of our lines, and this is why I think this is the more confusing of the two problems that I have like this. If I am going to row for a distance, and I row at a speed of 2.5 kilometers an hour, what do I have to do? How do I figure out how long that's going to take me? Disagree. So I know that I'm going to row for a weird amount of algebra of miles, because that's what we do in calculus. Kilometers, thank you. A weird amount of kilometers. But I know I go at 2.5 kilometers each hour. How do I figure out how long that's going to take me? How do we do that? Well, let's take it out of the algebra for a second. The question we're trying to solve, and I think this is another important problem-solving strategy, because I think that is a hard thing to ask. My question is, let's make up a number. Let's pretend this is, how many kilometers do you want this to be? 7. Love it. I love the decisiveness of picking a random number. So if I had to row 7 kilometers and I go 2.5 kilometers per hour, how do I figure out how long that will take me? What do I do with those to divide, right? DVD, right? That comes from, sorry if you guys are watching the video, I'm writing on the board. That comes from the idea that we know we've got 7 kilometers. And if you think science-y, I've got to use the 2.5 kilometers per hour, put the 2.5 on the bottom, right? Yeah. So the very science-y way of doing it is just a way to make sure that you know you're doing the right thing. So that's why we do 7 divided by 2.5. So the answer to our question is, what do we have to do with the kilometers and that rate to figure out how long it will take us? We've got to divide. So this problem ends up being the time that it's going to take me is the distance that I row divided by the rate at which I row, and then I've got to do the same thing for my distance on land, correct? So that'll be how long it takes me to row. This will be how long it takes me to walk. So 12 minus x over 4. Cool. So I have written a function for the time it'll take me to get to town. That function depends on what point I decide to row to. That's what the x value is. So how far away from P I decide to row to kind of locks me in place there. That's the thing I need to take the derivative of. No shortcuts here other than the fact that remembering, and I think this kind of threw a lot of people off on some of the earlier ones. When you see a quotient, I want you to say quotient rule, but I want you to take a minute and think to yourself, are any of the pieces of this constant? Because we don't need to do quotient rule here. That 2.5 is a coefficient, but it's a coefficient of 1 over 2.5, right? That 4 in the second fraction is a coefficient, but it's a coefficient of 1/4. So we really just have a function to find the derivative of that keeps its coefficient. So t prime is going to be 1 over 2.5 times the derivative of the function in the numerator. Root 9 plus x squared. What rule do I have to use? Chain rule. Find the argument. The argument is 9 plus x squared. So you guys know lots of stuff, which is just 2x when you take its derivative. So chain rule, I like to color code it. I'm backwards in my colors today. I always write the chain rule part in the other color. So it's 2x. Now I get to do times the thing I do with square root, which is 1 over 2 square root. Agree? All righty. 12 minus x over 4 is 12 over 4 minus x over 4, right? So the derivative of 12/4, a number, is 0. The derivative of negative x over 4 is negative 1/4, right? I know that was another thing that was getting us in some of those other problems. So when I am trying to find, I'll do this off to the side, you don't have to write this down, but the thing I'm saying out loud that might be easier to see visually, I am trying to find the derivative of negative x over 4, but I know that that is really just a coefficient, negative 1/4 in front of x. And if you just have an x term, then your derivative is just that coefficient. I think I found my t prime. Sure looks like I can do a little cancellation there, make life slightly more bearable. But I don't think this one's going to be super, super hard to solve either. We just have to clean some things up. I'm going to put those two fractions together, and I'm going to have x over 2.5 root 9 plus x squared. Get back to blue. And we want to set that equal to 0. It's not a huge leap. When you have two fractions being added or subtracted, bring one to the other side and cross multiply. So it shouldn't be a huge leap to rewrite this as x over 2.5 root 9 plus x squared equals 1/4. Bring our math back up here. 4x equals 2.5 root 9 plus x squared. I'm going to bring the 2.5 over to the left, which gives me 4 over 2.5. But I'd much prefer to have 8 over 5 because those are both whole numbers. I don't know if that was as good as I wanted it to be, but it's what I chose to do. I can square. I'm going to have to square both sides, so it's easier to square 5 than it is to square 2.5. So I just doubled the numerator and the denominator, which gives me the same fraction. And now we'll square both sides. 64/25 x equals 9 plus x squared. Sure feels like a job for the Pythagorean theorem, or for the quadratic formula in a minute. Let's see what we get. Is there a better way to write 64/25ths? I just think I multiply it by 4 and just because we're gonna end up going for our calculator at some point. Yeah, 256 over 100. So let's do that. Again, actually, I mean, I'm doing it mentally, but if you type in 64 divided by 25, you're going to get the same result I'm about to get. So times 4 gives me 256 over 100. X equals 9 plus x squared. But that's just 2.56. So we will write x squared. We're going to subtract it because we're bringing it over to the other side. But I'm going to write it as 2.56 plus 9, x plus 9 equals 0. And we can say that x equals 2.56 plus or minus the square root. And feel free to pull out your calculators and type away. 2b squared, 2.56, but negative. Not that it matters because we're squaring it. Minus 4 times a times c. Sure would be nice if this had come out to something that was actually real, wouldn't it have? I don't think 2.56 squared is going to beat out negative 36. Yeah, that's not good. Turns out we've been imagining this island all along. It does not exist. So we got to find the mistake. Remember when I said earlier that I should have done this one before class? Still stands. 8/5 4x. Or x squared. Oh, I see what it is. Haha, we didn't need the Pythagorean theorem at all. I forgot to square the x. When I squared 8/5.
Oh, yeah.
Yep. What do you do when you make a mistake? You find it. It's math. What makes good math students? People who can do stuff like that. This still feels like it's going to be a disaster. So we're going to have negative coefficient times x squared equals 9, which, oh, no, we're not. Nope. No, we're going to have 1.56 x squared equals 9, aren't we? 2. Yep. 2.56 x squared minus x squared equals 9, just so I'm not doing stuff in my head on you guys. 1.56 x squared equals 9. And that means that x squared equals 9 over 1.56, or x equals, we're not going to put minus, so the positive, because it wouldn't make sense to call the distance negative. Root 9 over 1.56, which is a number, 2.40. Is there a third decimal point? Cool. 2 if you round, 1 if you truncate. Both are okay. We follow AP scoring. Yep, three digits, round or truncate, all as well. Truncate because they allow you to write all the digits if you really want. There's always that one weird guy that does that. So, or gal. So yeah. So the answer to this question, where should the boat be landed so that the person arrives in town in the shortest amount of time? It would be 2.401 kilometers from point P. That would be the idea. You know what I mean? If it were multiple choice, it would be, you know, I don't think this would be set up as an FRQ because they would. So we found x, which is the distance from point P. And the question says where.
Yeah.
I think we're good. Yeah, we didn't ask us for the distance. You are correct. If it says, if it said how long will it take him, you would have to plug into t. Yep. It wouldn't, if it peculiarly asked what would be the total distance traveled, you would plug it into this plus this. But I don't think it would say that. So the reason that's the shortest distance, we are in a situation where we only have one critical value. The other critical value is negative, so that doesn't make sense. That would mean you're literally boating to somewhere further than P. So that would be the other critical value. You have one critical value. We should show that our T prime, I guess we could do a test on both sides of 2.401. So let's do our, let's find the T prime of 0. And let's find the T prime of some other convenient number so that we can make a sign chart. I mean, actually what we could do, here's what we could do. Instead of the sign chart, I'm looking at the derivative, and this derivative is not something that I can easily make a sign chart out of, right? So let's do EVT. Let's make a table. Let's find the time it would take for x is 0. That's one extreme case where you literally boat the 3 kilometers straight down and then walk the full 12 kilometers to town, right? That would be what x is 0 would be. What's the other extreme case? What would x be? Boat straight to town. What's the x value for boat straight to town? 12. Yep. Because that makes that bottom red line 0, which means you're boating straight to town and then going 0 kilometers to town. And our number is 2.401. So we will now find t for those 3 values. Yes? Boating straight to town, that column is the x value. So if x is 12, the amount of distance that you walk on land is 12 minus 12, 0. Right? Which means that you've boated to town with 0 miles or 0 kilometers left to boat. Yeah, it's weird because I'm not answering how long did you boat. I'm asking what's the x value. So the largest x value we could get as the smallest x value we could get as an answer would be an x of 0. That would mean that the black line is 0 and the red line is the full 12. So that's one extreme. You boat 3 down and you have saved 0 walking miles. Kilometers, I keep saying miles. All right, so that's one extreme. The other extreme is that x is 12, which is supposed to mean boating straight to town. So x is how much distance you've saved walking by boating. I think that's what it really comes down to. What is x, right? X is how much distance you've saved walking by boating diagonally. If I boat directly to town, I've saved the full 12 miles of walking. Does that make sense? I don't think so. I can tell. I always tell by the look on your face. Right.
Good morning, teachers. Sorry for the interruption. If you wouldn't mind, please look around your classroom.
Oh.
And any students that are not dressed up,
All right.
those students wearing a hoodie, not wearing a collar, or wearing sweatpants in front of the auditorium at this time. Thank you.
Yep. That's good. That's good. No problem. Yeah. The most extreme x could ever be, and I mean, another way of thinking about it is we're measuring distance here, and distance could never be negative, right? If x is less than 0, I'm saying that the distance of the black line is negative, correct? This isn't as much of a y, but just the math kind of locks it in place. If I make x bigger than 12, then the red distance is negative. So those are my endpoints. X cannot be x, the distance I've saved by rowing diagonally, cannot be any smaller than 0, and it cannot be any bigger than 12. It's another way of thinking about it. So we need to get our T of 0, our T of 2.401, and our T of 12. Franklin's plugging away. I hope everybody else appreciates them. What do you have? Okay. So this would take 4.2 hours. Cool.
And then ours is 3.9.
There we go. And that is, I'll squeeze that up. That's a 948 at the bottom. Let's see. Yep. Which should make sense. You're boating so slow that going straight to town is going to take you the longest, right? It's a significant slowdown from 4 kilometers to 2.5 kilometers an hour. You save a little bit by doing the boating diagonally, not a whole lot, 0.3 of an hour. But if you're planning on a 4-hour adventure, it will take any minute we could take, right? But yeah, that's the answer to that one. The one that you have that's like this will be a little bit easier because I'm not giving you speeds, but I'm giving you prices. So the things that I give you in that one are going to interact differently with the algebra. So when we said you've got to divide by 2.5 and divide by 4, you're going to be doing something else with those numbers in your problem. And there aren't many other things else that we would do. So if we didn't divide in this, if we divide in this problem, what are we probably going to do in your problem? We're doing something different. It's multiply. Yeah. Because it's still going to be a rate, and rates can only do 2 things. Oh, I feel like I'm in period 2 because this is what I'm trying to bring in the 9th graders' head. 9th graders, algebra enhancement. But I'm trying to get through their heads that rates are either meant to multiply or divide. So anyway, okay, so let's press stop.